So today, lesson 2, we're reviewing concept of kinetic energy and potential gravitational energy. So we already talked about that work and energy are related together. And the first type of energy we're going to talking about is the object that are moving. When something is moving, it possesses this thing called the kinetic energy. And the equation, where it came from, it's from here. If you wanted, we can just work it through. I know that work is force times displacement. And from the beginning, we have learned that F equals to M times A. So if I sub this into the F, work is mass times acceleration times the displacement. And then from before, we have learned from the kinematics that Vf or V2 squared equals V1 squared plus 2A delta D. If we were to rearrange this equation for A and D, because we wanted to replace the A and D into the equation, so V2 squared equals V1 squared plus 2A delta D. And if I'm rearranging for these, I'm going to have to bring the V1 over by minusing. Right, so I can bring this over. So this becomes V2 squared minus V1 squared plus equal 2A delta D. Bring the 2 over by dividing. V2 squared minus V1 squared over 2, it equals to A times delta D. So I'm replacing the A delta D in the work equation by the V2 squared minus V1 squared, and this is where they came from. So work equals to mass times, instead of A and delta D, we're going to sub in V2 squared minus V1 squared over 2. Okay, so that's what work can be equaling to this. So let's just clean it up. So we're going to be separating out the 2. The 2 is in the denominator. So I could write it like this. So all I did is I took the 2 and I put it underneath each of them. And I can also multiply in the mass into both of the terms. So mv2 squared over 2 minus mv1 squared over 2. And sometimes it depends on which teacher you have, right? Sometimes it can also be written as 1/2 mv2 squared minus 1/2 mv1 squared. So this is the deriving of the kinetic energy equation. So the final speed squared times the mass half minus the initial speed half. Okay? And this is where they go about. So things that you should be noticing, you should know this equation, and you should know that EK at a particular speed is 1/2 mv squared, and work is always change in energy. And we talked about this yesterday. We call this the work energy theorem. It always equals to the change in energy, and in this particular case is change in kinetic energy. And later on you can have work equals to change in potential energy, work is equal to change in elastic energy. So anytime when there's a change in energy, we can say that it equals to the work done. Okay, and as work, kinetic energy is also considered to be a scalar quantity, and it has the same unit, which is capital joules. For example, what is the speed of the electrons in a television tube if the mass is 9.1 times 10 to the negative 31 kilogram, and the kinetic energy is 9.2 times 10 to the negative 18. So this is a test. Do you know how to rearrange the equation, and do you know how to punch things in for scientific notation? So speed of the electrons. So I have the mass, which is 9.1 times 10 to the negative 31 kilogram. And the kinetic energy, EK, is 9.2 times 10 to the negative 18 joules. And they're asking you what is the speed. So I have EK. I can use the EK equation is 1/2 mv squared. So 9.2 times 10 to the negative 18 equals 1/2 mv squared. So to solve for this, You don't have to show any of these work, okay? Like you can, if you can just punch it in the calculator, get me a V, that's all I care. I'm going to change color just to make sure. This is divided by 2. So to bring it over, it becomes multiplied. So I'm going to take 2, multiply it by the 9.2. And then this is multiplying, so I can bring it over and it becomes a dividing. So divided by 9.1 times 10 to the negative 31, and it equals to v squared. So to solve for v, you have to take the square root of everything. So now it's time for you to remember how to punch it in the calculator. I just want to make sure that you use the right button. Whenever it's times 10, we would replace that by either the EXP button or the EE. Sometimes you have times 10 to the X. Those are the button that you're replacing. All right, so just to show you, the button is this EXP button right here. So what I would do is I would go 2 times 9.2. Instead of times 10, I would press the EXP button on my calculator, and then I would press negative 18. See how I didn't type the times 10? Because the EXP button would replace this times 10 right here. Okay, and then divide it by 9.1 EXP negative 31 equal. Okay, and then finally I have to take the square root, so I would take the root of whatever the answer that I got, ANS, and it equals, so the answer worked out to be 4496640, blah blah blah. Okay, so the speed that we got from the calculator, I'm going to write the whole thing out and then we'll round it to the proper sig date. So 4496640.993. That's the speed that I got. And so check the answer. I want 2 significant digits. So that means I need to round it to the proper scientific notation. This is a huge number. I appreciate it if you put it in a proper format. You can leave a whole bunch of zeros too. I won't mark that wrong, but it'll be nice if you express them in, nice little format for me. So 4.5, so you always put the decimal place after the first non-zero number. So if I were to put a decimal place, I would put it right here, right? The first non-zero number, and then you have to count how many times. 1, 2, 3, 4, 5, 6. So it moves 6 times before it gets to that spot. So it becomes 4.5 times 10 to the 6 meters per second. This is scalar, so no directions. Next one, how much work? I need work must be done to accelerate an 800 kilogram car from 15 meters per second to 30 meters per second. So the question asks for what is the work done. They give you the mass. So then the first velocity is 15 and the second velocity is 30. And they want work done. So if you go back to the equation, I got mass, I got V1, I got V2. This is probably the equation that you're going to use, right? The work done is the change in kinetic energy. So 1/2 mv2 square minus 1/2 mv1 square. So it's a straight plugged in. So 800 v2 is 30 minus half times 800 v1 is 15. Punch it in your calculator. This is a straight plugged in. There's no rearranging for this. So I got 270,000. Check significant digits. There is 4 here, 3 and 3. So I need 3 sig digs. So 2 point. Okay, let me just write the full answer. Make sure we're all getting this. So I got something like this on my calculator. So if I want 3 sig digs, 2.70 times 10 to the 1, 2, 3, 4, 5 joules. This is the one you must express in the scientific notation, or you won't be able to do the 3 sig digs, right? Sledgehammer has a mass of 4 kilograms. It is moving down at a speed of 6 meters per second when it strikes the fence post. It drives it 10 centimeters further to the ground. calculate the kinetic energy of the sledgehammer, and then the average force exerted on the fence post by the hammer. Exerted on the fence post by the hammer. Please assume 2 signics for this question. So right there, what I have the mass is equals to 4.0 kilogram. It's moving down at a speed of 6 meters per second, and it drives it a displacement of 10 centimeters. I hopefully right away you know you need to convert it to SI unit. First question asks, what is the kinetic energy of the sledgehammer? And part B asks, what is the force exerted on the fence post by the hammer? Okay. So first one, EK. Equation for EK is 1/2 mv squared. So 1/2 mv squared. So 72 joules. Okay, part B is relating to the force. Okay, force is relating to work. Force does not directly relating to EK. You can't just say F delta D is equal to EK. You have to relate it back to the work. So work is force delta D, and I know that the work is also equals to the change in kinetic energy. You calculate one of the kinetic energy, okay? And this is EK1, okay? You could calculate what is EK2. Do you know what is the final speed of the sledgehammer? All right, so let's think about this. You have a fence post, and the hammer comes and strike it at 6. Okay, the initial velocity of the hammer is 6. And then what happened is, then by pushing it down by 10 centimeters, so I'm able to move it by 10 centimeters, what is the speed at the end? It is 0, okay? Because like once it moves it for 10 centimeters, your hammer stop. That's how much work it has done. If you need to do it again, you're going to raise it back up and slam on it again, right? So your EK2 is actually 0, okay? So from here, we're going to keep working. So F delta D is equals to, I'm going to write EK2 minus EK1. I'm not going to bother with the equation that we used in the last example, just because I already calculated EK2, and I mean EK1. Okay, so I'm just going to write, since V2 is 0, EK2 is also 0. So F is given, no, F is what I'm looking for. Delta D is 0.1. It equals to EK2 minus EK1. F is equals to negative 72 divided by 0.1. So negative 720 Newton. Now what? Why negative? Okay, so think about the values, right? The initial velocity is 6. It is at 0. This is the force that is actually acting against the sledgehammer. Okay, so to actually figure out what is the force acting on the fence post, it is going to be 720 Newton, because it's the action-reaction force. So I'm going to rewrite this out. Okay, this 720 is actually the opposite force that is causing the sledgehammers to slow down. Okay, so it's force on the sledgehammer. Hammer. Okay, and to find out what is the force on the post, it's going to be 720, which is the reaction force from the hammer to the post. Okay, so it's positive. Now moving on to the basic equation for gravitational potential energy. Okay, and it has something to do with the position of it. If you lift something high up, it has the ability to do work and fall. because you're going against the gravity. So gravity actually have a field, that the force field that is allowing this object to gain some of this energy called the potential energy. Sometimes we call it the store energy. Okay, so it does require my work to lift something up high, but once I've done that, I'm storing energy of this object that I've lifted up high. And so the equation deriving is fairly straightforward. So it started off with, oh my goodness, it started off with work is force time displacement. And since I know that when I'm lifting something, the force is mg, and delta d, in specifically, we're talking about the height. So we just plug it in the equation. Work is mg delta h. And cleaning it up like we did just now, this time, the delta h is actually the change in Eg, okay? The change in the gravitational potential energy. So that means work can be changed in Eg, and work can also be calculating as Eg2 minus Eg1, and in particular, the potential energy at any spot is mass times G times H. Okay, so just wanted you to have more. You could use this, or this. Those are the three equations that I would use. And keep in mind, gravitational potential energy has everything to do with where your reference point is. Okay, so if I have an object, I toss it up and then I drop it back down. It all depends on where you want it to call the zero. If I call h equals to 0 at this point, okay, this is a positive height. So height here could be, I don't know, I'm just making this up, can be 10 meters. Okay, but then if this is 0, the height at the bottom here could be minus 20. But I can totally change it around if I say, hey, I want to change my point of reference, and I want it to call height equals to 0 at the bottom. If that's the case, this height is now 20 and this height is now 30. It's all a relative things, and they measure with respect to each other. So 1,000 kilogram roller coaster moved from point 1 to 4. Okay, so it goes all the way here. It gives you all these numbers. Okay, they're asking you what is the gravitational potential energy at 1 relative to 2. Okay, what relative to 2 represent? It means that they want you to set number 2 as the height equals to 0. Okay, so if I set this height to be 0, 0.1 would be at a height of 35. So question A, the gravitational potential energy at 0.1, I would use the 35 for the height. So mgh, so mass is 1,000 times 9.8 times 35. So 343,000. So with two significant digits, I'm going to write it as 3.4 times 10 to the 5 joules. Part B. I now need to find the gravitational potential energy at 2 relative to 3. So relative to 3 means I make 3 height equals to 0. And so what is 2 then in comparison at 0.2? If h is 0, it's below it. So the height for 0.2 is negative 28. And so to work out the gravitational potential energy, it is mgh. So mass times 9.8, and this times the height is negative 28. So with 2 signigs, negative 2.7 times 10 to the negative 5 joules. Last question. Calculate the change in potential energy when it goes from 3 to 4. Okay, so I want the change in potential energy. So the question specifically is asking for what is the change. So this is mgh2 minus mgh1. And now it's up to you. What do you want to call the height for 2 and 1? I'm just going to erase the other mark. Okay, so I'm now starting fresh and looking at between 0.3 and 4. So 0.3 and 0.4. Okay, it's up to you how you want to label what is 0, what is not. Okay, so on the numbers, they have 15 and 28 for you already. So the easiest thing to do is if height is 0 here, then the height in here is 15 and the height in here is 28. Okay, I would choose to do that because that's already in there. But if you don't want to, and you say like, well, I know I want to set number 4 as 0. It's up to you as well. If you want to do that, you can set number 4 to be the height of 0. But if that's the case, you're going to have to subtract the 28 from the 15. So the height here is 13. So notice the change is still the 13, and it's up to you what you wanted to use. So now h at 0.3 is going to be my h1 because that's the starting, and then the number 4 is going to be my h2. So when I sub it into my equation, it'll be m g h2, which is 15, minus m g h1, which is 28. Punch it in your calculator. Okay, so 127,400 joules. Put it in the right signigs. I would put 2 significant digits, so 1.3 times 10 to the 5 joules with a negative. Okay, so what do you think the significance of negative is? The change in energy, I went from a higher gravitational potential to a lower, so it makes sense that I have a negative change, right? Like I'm losing the energy. And later on, or if you remember from grade 11, these energy that are lost has now been converted to adding kinetic energy, right? So we're going to talk about conservation of energy later, and it will make sense.